Cool. So I'll start. I am Nish. I was a PIBBSS fellow last year, and I was also half of the year. And I'm going to talk about some of the works that I've been doing, the more recent versions of them, and I might relate them back to the things that I did last year. For today, the main part of the talk is going to be about a solvable model of in-context learning. So I'm going to present a kind of a simple toy model of a transformer architecture where one can completely analytically get handle on its training dynamics, the algorithm it learns, and so on, and try to gain some insight about the transformer architecture and what it can do when trained. Cool. So this is going to be the outline. There's roughly 4 parts. I will give an introduction to transformers and some observations that relate to the work, followed by the model. This part will be long, explaining the model, various parts of it, and so on. And then another long part of analysis where we'll look at kind of how the model learns, its dynamics throughout the training period, and what it ends up learning, and how it can do in-context learning. And finally, there will be some empirics on like verifying the model against simulation and relating it to perhaps more real-world kind of model. And then I'll end with some conclusions and thoughts on future work, limitations, implications, and so on. I wonder if I can make my cursor.
Your cursor is visible.
Okay, cool. Okay, so introduction. The transformer architecture is sort of the cognitive apparatus that has made modern LLMs so successful and kind of increased our concern for its risk and kind of drastically scaled up its abilities that we have seen lately. And they sort of belong to a new family of generative models that don't require strong supervision. So this is kind of trying to make a contrast with older models from deep learning era, which were trained with very heavy supervision. These were mostly like vision type model where there was a lot of labeling and like very direct supervision, as opposed to these modern transformer and diffusion type of models. And this newer generation has turned out to be surprisingly capable. In particular, for transformer kind of things, their architecture allows for responding to arbitrary sequence of input and produce an arbitrary sequence of output, which is in a pretty stark contrast to the kind of classical things of like input-output relationship that you see in vision model or something like that. And of course, this is the kind of reason it naturally fits into the language modality, which is basically a sequential object. And they're trained using massive corpus of data and basically with very little strong supervision. And during the training procedure, various parts of the data is masked out and you're asked to predict by using a context. So even from the get-go, they are trained to kind of fill in the blank by being aware of the relationalities and the context that the data is appearing in. At least the first pre-training, as they call it, the whole process is just filling in the gaps of language type of data and inferring the gap, what should go in the gap from the context. This belies like crucial conceptual differences to these classical deep learning era. It's classical in the sense of that there is some transition into new kind of thinking about it, but it's not really classical in the sense of how much time has passed. So sort of the first difference that one can vaguely point out is that in modern era, these more transformer type of things learn programs as opposed to mappings. And this will be kind of point that I'll return to again and again, which is that like classically, you could think of these models as some sort of function that maps some input to output, but transformers operate on the context, on the relationality, and they act as an algorithm that adapt to the context given to them. So it's sort of, in some sense, a meta thing where it not only does input-output mapping, but like adapts to the context that it's given. So sort of like a program. And it matters not just the content of a thing. It's not that this picture has a cat, so I say call it a cat, but the fact that the cat appeared as a word in a sentence, that appeared as a part of a text, and so on matters. So it not only captures some like intrinsic content of data and object, but also kind of reads out and responds to relationships in the data. And it's gives rise to is a phenomena people have called in-context learning. And this phenomena can be sort of described as like, you have a model, you trained it using whatever procedure and data that you have, and you have the model frozen now. And then you try to see if the model can do a task that it has not seen before, but you provide it with a few examples in the context. So you literally, as you'd speak to a person, give it a few examples of some sort of relationality or some sort of mapping that you'd want the model to learn. And then surprisingly, it can do that in various contexts. And various people, including big companies like Anthropic and other places, have kind of emphasized that this is perhaps the core reason underlying the various successes and abilities of these language models. And I think the fact that this is something so fundamental, which is to kind of react to the context and adapt to it, is kind of argued as a reason for the success, should give people in AI safety a pause, because it is the kind of ability that one would kind of, if not enough, but I would think necessary for AI to pose serious threats. And just to give an example of what I mean, I'm like transformers, for example, trained on a language it has never seen here, Welsh, for example, we can give it 2 examples of the sort, like existential to this Welsh word, danger, and then it can map an unknown word using this mapping. In fact, there have been examples that, given enough example, it can learn new languages that it has never seen before. And that is all without changing the weights, without doing any kind of gradient descent or parameter tuning. And more generally, to kind of think about it abstractly, given an example of n relationships, x1, fx1, where f is the relationality, and we give it an example, then we ask a query and ask it to predict what the output would be. And if it gives an answer fx query, then we would say it did an in-context learning. And these relationality might be the kind of relationality it has never seen in its training data itself. So just to make the point one more time clearly, during its inference, not during training, at inference time, these transformer models act as learning algorithms that kind of apply their algorithmic process on the data and learn some arbitrary new mapping or relationality in the data without ever having to change their weights and plasticity. And in some sense, even just thinking about it, it's a pretty striking phenomena that this is possible. And we would like to get some handle on it. And this is, and I will present a very simplified model where we can get a handle on it. But before doing that, I'm going to give a few more general thoughts on how to go about even trying to handle these theories. At least these are my thoughts. And this starts from observing that these models, transformers-based model, are very phenomenology rich. That is that you observe very intriguing and interesting phenomenology when you look at them, and I mean things like in-context learning. And there's a wide class of these things, Brookings and so on. And they are also very complex things with moving parts. You know, there's data, there's pre-training, post-training, tweaks in the algorithm, tweaks in the training process, and so on. And all these details are not so natural to be captured precisely and mathematically. And this, in some sense, is a problem not only unique to theorizing about transformers or AI models. They're in physics, in kind of condensed matter physics, and to some degree neuroscience, which is my we operate in this regime where we measure some interesting phenomenology. We know some details about the mechanism, but there are way too many of them, and we want to get some understanding of them. And what we usually resort to doing is to recreate phenomenology with minimal models that stay true to some elements of the underlying complex things. Some examples are like magnetization in spin glass. This is a very famous example of like very simplified theory that captures a lot of interesting phenomena in statistical physics. Spike tensor model for like kind of understanding signal recovery. In neuroscience, people have come up with various models for working memory, continuous attractors, and sort of how different neuron classes, excitation and inhibition balance themselves and so on. So all of these models have in common that they aim to explain some interesting phenomenology without being completely honest about the microscopic detail, but preserving something essential of the real world thing. I think this is perhaps the way to go forward for theorizing about transformers as well. Yeah. And as I said, by design, they will be able to capture and explain some part and not address other. And I think in some sense, this is a feature because it allows us a little bit finer grained understanding of the relation between the details of the whole thing versus the phenomenology that you observe. But at the end, it begs the question, what phenomenology to choose? These are complex things with many, many interesting behaviors. So in some sense, choosing what to model and for what kind of toy model to design is sort of aesthetic or a practical decision. And that has to be motivated by some goal, for example, in our case, helping evaluations or steering the model and so on. And I will get back to these at the end. And just to say from the get-go, these models are going to capture something. In our case, is going to capture various nonlinear training dynamics, but it will not capture various other things. For example, optimization, properties of the learned function, real-world structure, various training details, and so on. In our case, and we will get back to these limitations again. Cool. So this is where I'm going to begin with the meat of the talk, It begins with considering attentions and attention head, which is the crucial architectural innovation that kind of powered and gave rise to transformers. So abstractly, if we consider a sequence of length n, so we have n elements in a sequence, and these are all vectors in D with sets of length n. Then a transformer head, sorry, an attention head is then defined using some nonlinear function phi. It's usually softmax, as this equation here, where what you see is this nonlinearity is applied to a quadratic form. So the z, the data appear twice on left and right, and on the middle is this wk, wq term, which are the so-called query and key matrices. And in some sense, what we're doing is we're going to be projecting all the data into the basis formed by wk and wq, that is each column of the z, z1, z2, and so on, and kind of measuring their similarity in their basis, in this basis, and taking some sort of empirical average of it. And like conceptually, this was kind of motivated by trying to understand the relationality between various pairs of Z1 to Zn, right? We want to see which elements of these sequences are like each other, and we would like a way to capture the similarity. And in transformer model, Wk and Wq are going to be trained. These are the parameters that will be trained. And in our case, we will simply consider a linear attention. That is, we will remove this phi, or just the phi will be the identity function, and we will simply look at this quantity, Z transpose WKQZ. And this will massively simplify our life, and it is actually what will make solving the model exactly possible in the first case. But what you'll observe already is, despite a linear nonlinearity in the attention head, the function itself is still nonlinear in Z. It appears twice. It's a quadratic function in it. So just the fact that this softmax operation becomes linear still keeps the model highly nonlinear. So given this introduction to the attention head, we can more broadly define transformer model, and we're going to look at one layer, one attention head only transformer. And the full model from end to end can be written as follows. So FZ is the model, it's the output of the model, and it's going to take the original input Z, the sequence, and looking from the right, it's going to apply the attention mechanism, and then it's going to dot product the attention with the data itself before, and then going to apply another matrix, which is called the output matrix, WP together. And in our case, as I said, we're going to look at the identity nonlinearity, and the whole thing will basically boil down to something like this, where we have this like 3 appearances of Z in the processing of the data by the transformer. And this is the model that we're going to be analyzing. So this is what I call a linear transformer, where we have replaced the sigmoid nonlinearity with identity function. And like I said, we have chosen linear attention, but the model is still by itself highly nonlinear. Okay, given this, now we want some kind of task, and transformers can do a variety of tasks, but we want some kind of simple task where we can try to get a handle on the in-context learning behavior. So the task is some sort of like simplest possible thing you can imagine, which is a regression. So at inference time, which is, suppose the model has been trained, these parameters that we saw before, WK, WQ, WP, WV have been trained. At the inference time, the model is going to observe n pairs of d-dimensional data, xi and yi. So they are related to each other, and they are both d-dimensional. And then we're going to ask it to predict the output yq for the query xq. So we basically want it to learn the relation between x and y so that it can predict the output for the input query. And this is at inference time, so no parameters are being changed for this. And to simplify the life of this model, and also for us, we're going to do embedding in the following way, where we're going to simply stack the x and y vectors on top of each other as columns, and we're going to define the z, the sequence of inputs, as the follows. Basically, d by d, 2D dimension, x1, y1 in each column is going to be related to each other linearly, and we're going to show the model n of these examples. And at the end, we're going to ask the model xq. And for the yq, which we want the model to predict, we're just going to give it a 0 so that it has to fill in that value. What should be the value? So basically, the output of this model should fill in the 0 with what should be the yq, the true relationship. So again, graphically, and this is in just one dimension to show an example, at the inference time, we're going to show model x1 to y, x1, y1 to x and yn, which have this linear relationship. They fall in a line. And then we're going to give it xq and 0, which is this red dot on the left. And the job of the model is to predict xq, yq, the red point on the top. So it needs to fill in those 0 value to give us the right value. And of course, this is done in some dimension d. Cool. And now get the problem set up more clearly. We're going to sample these x from here, these x values. From multivariate Gaussian distribution, we're going to allow there to be some correlation between them. But for the sake of this talk, I'm going to take all these matrices to be diagonal matrix because it will simplify the presentation. It doesn't have to be that way. At the same time, we're going to define W, the weight that relates X and Y. And this is also going to be a diagonal matrix whose diagonal values are going to be sampled from the standard Gaussian. So the model will then be trained with SGD, stochastic gradient descent, using M training tests. So we'll basically sample M relationships, which are these W's. Wm goes from 1 to M, W mu goes from 1 to M. And we're going to use these samples to train the model. So, and after the training, the output of the model, as I said, is going to be the final column and the bottom part of the column. And this is what I'm showing here. The output of the model, that is the prediction for the xq, can be read on, and in particular looking at its bottom d dimension where the y should be. So basically the prediction of the model will be this y hat. And the first part goes away because we put 0 there in the n+1 column, and only the second part remains. And this linear transformer basically predicts the output in the following way. And what we have done here is also to simplify these matrix WK, WQ into WQ, because these are two matrices, so we're just going to replace with one, WP, WV as just WP matrix, just to make our life easier. But essentially, it doesn't change the expressibility of the model. It's just two matrices, which is can be replaced by one matrix. Okay, with all this, now all we need to kind of finish the model is the loss function. We're gonna do a mean square error loss, which you'll note is different than the standard loss used in transformers, which is next to. But we are n+1 token that only cares about the n+1 position in the context. Yeah, and the parameters are initialized close to 0, either randomly or deterministically. And finally, we have a regime where we want to be, which is the learning weight should be small. Basically, the idea being we have this M training example, so the weight should change minimally at each presentation, and we're going to do a mini batch of size 1. That is, each example is presented one at a time. So, and each one doesn't change the weight by too much. But at the end, when the model has been presented with all M example ones, there is some appreciable change in the weights. And we're going to repeat this again and again. So naturally, we're going to kind of measure time in terms of epochs. How many times have we presented the model, the whole set of M examples? And mathematically, for some parameter theta, this can be WP, WQ. It's a dummy variable. We can write on the left, this is the SGD or descent dynamics with a learning rate. And one average over all the samples from 1 to M, we're going to say that we took one step in updating the weights. And then we're going to take a continuous approximation of this. Cool. So having set up all that, we're going to start with the boring, but the result that will kind of simplify our life by a lot, which is model reduction. So effectively, if you stare at the predictor we had before, this y hat, you will notice that only few parts of the model matter. And furthermore, if you analyze, and this is a lemma, it's not obvious, and I'm going to skip that. If you analyze the dynamics, parts of the model will parts of the parameter will simply end up being 0. So here I'm dividing this WP, which is a 2D by 2D matrix, into these D by D blocks. And what I'm claiming is that the top half of the WP and the right half are basically going to be 0 due to the fact of how we have kind of organized the problem, and that these parameters simply don't play a causal role in the predictor. The kind of a darker 0 is 0 because at that point, the global minima of the SGD dynamics takes it to 0. So these parameters are going to be set to 0 by the SGD dynamics. So really in this 2D by 2D matrix, both of them, there's only a D by D section where we're going to get some non-trivial evolution. And I'm calling that part P and Q. And with this P and Q, we have a sort of an effective reduction in the predictor. So the linear attention transformer model gives a predictor for a query XQ, an example, and a regression task mu, the predictor y hat mu will look like the first equation there, where there will be P, and this sigma hat, which I'll talk about, Q, and then XQ. And then sigma hat is simply remember that in this action task with some covariance structure sigma, and sigma hat is basically the empirical covariance that the model estimates by just looking at the input during inference time. And in fact, this Z by Z times Z transpose term that we saw earlier can simply be written in terms of the weight of that particular task times this empirical covariance matrix. And this will play a pretty central role in what comes this sigma hat. Cool. So non-trivial parameter evolution. I showed you, and I'm going to ask you to believe me on word because it's just a technical lemma, that there are these two parts that matter, P and Q. And these two parts, again, their dynamics have both like update, for example, on the left, SGD update on the right can be written like that. And if you actually take the derivatives of the P, I'm going to do it for P, but because P and Q are pretty symmetric and we can write Q easily given P. So if you take the derivative with respect to P for the loss, this left-hand side quantity, and take an sort of average over mu, you get the following quantity here. And there we need to take one more average. And interestingly, what appears is a random covariance matrix. So Wishart random matrices are kind of models for random covariance. And this appeared because if you think about it, each training example, the model needs to care about the covariance of the data it has seen. And in each training example, there is a different covariate which has a true underlying covariance, the true sigma. But at each example, it's seeing a slightly different sigma, which interacts with itself and becomes sigma square. So sort of we need to take an expectation of this random matrix, basically. And we can do that. And basically, once we do that, we get these two terms, kind of symmetric if you look at the right-hand side term in the bracket, and the difference is P and Q here, like differently on the side the term here, but you basically get this dynamics for P and Q. And right now it looks a little involved, but we'll look at it in more detail in a second. So we get this kind of a differential equation of P and Q, but they're highly coupled. As you see in the differential equation for P, there's P and Q, and for Q, there's both P and Q, and we need to kind of try to solve it. But before solving it, we can already get the fixed points. So just by staring at this dynamics, the left-hand side will be 0 basically in two cases, either when P and Q are 0. And these are the cases where if you look at the loss landscape of the training, P and Q are 0 are the saddle points. So it will not stay there. At some point, the dynamics will take it away from there. And the second fixed point is the global minima. I will not prove that it's global minima, but it is. And it basically comes as the inverse of this term, right? For this term in the bracket needs to be inverse of this, such that the whole quantity on the right becomes I and the whole thing becomes 0. So simply from there, we get a prediction for what the PQ star should be at the global minima. And it is this quantity. And it's basically, if you look at it, it's almost close to the inverse of the data X covariance, but with some correction factors. And if you kind of substitute this back into the predictor, you get this quantity. And just by looking at it, it's not obvious what it means. But if we kind of take the limit, for example, in the limit of large n, where n goes large, meaning that for each example, we're showing many, many, many examples, and we expect the model to do very well. Indeed, this fixed point term at large n limit, as you will see, this is 1, this becomes 0, you get sigma inverse. Similarly, at an infinite limit, this covariant empirical covariance sigma hat also kind of concentrates to the true covariance sigma. So if we substitute it back, what we get is the predictor y star is sigma inverse times sigma, and W, which is the true kind of relationality that the model was able to infer, times xq. So exactly we get that the predictor is exactly equal to the true value in the large n limit. So that's sort of a sanity check. And now we can try to reason about it, like what exactly is this algorithm that learned to do this in context regression. And the way I see it, there's two parts to it. The first is it kind of widens the input. This is this inverse part. So what it does is it looks at the data, and there's these X values, and it says there is some correlation between them. First, let me just remove this correlation. Like, let me just widen the data. So it does this by this kind of fixed point quantity. And once it does that, then basically it becomes easy for it to just get the relation between X and Y, right? It's like now you've set X to be all 1 and Y to be some value. So the W, the effective weight matrix, will simply be the leftover W once we have set X to be 1. So it's something like that going on, where it has whitened the X, and then it can infer the contextual weight matrix W mu. and then do its prediction. But still, there for finite n, which is the more realistic case, there are two sources of error. The first one is this trace quantity here, which acts as sort of effective regularizer. So we didn't add any regularization, but at the fixed point, the model self-regularizes using this trace quantity. And in fact, if you look at it, it will kind of make the model invertible. It will keep the model invertible. And on the right-hand side also, this is an approximation. So sigma hat need not be exactly equal to sigma. There can be like finite corrections to it. So that will also give rise to error. So the error of trained model in linear regression, which is going to be small, but non-zero, comes from these two factors. And sort of, I need to speed up, but sort of an interesting observation is, in fact, if you look at it carefully, you'll see that what this model end up learning is actually effectively doing one-step gradient descent on the input, even though the weights are frozen. So if I were to give you a problem of solving this regression task, algorithmically, you would minimize some sort of least square problem like that. And in fact, if you don't do perfect minimization and only take one-step gradient descent, with some preconditioner, that's some kind of scaling, eta, you will find that it actually, for some choice of eta, which in our case has to be this quantity that we saw before, it exactly matches the algorithm that the frozen weight linear transformer learns. So again, for some training sample that this model sees, and after the weights are frozen descent without any change of parameters. And in this way, it's able to kind of learn and actually do like pretty well in these regression tasks. So next, there are these conservation laws. Basically, what happens is that because of the way the dynamics are structured, there is some conserved quantity, which is going to be this difference of norm. I will not go through the steps of derivation, but it's there, and you can show that this quantity is going to be conserved throughout the process. But the bigger point is, the moment there is a conserved quantity, it means you're basically in a degenerate landscape. Something is not changing. So you're not exploring the whole landscape. You're in some kind of singular area, as SLT people would say. And in fact, once this particular conservation law kicks in, which is actually can be shown to be true for even nonlinear transformers, the only freedom you have is not P and Q individually, but only the P and Q. So each P and Q can be written as this conserved quantity and PQ. So all that matters, meaning the only degree of freedom you have is this kind of PQ quantity. Cool. Now, having said all this, let's actually go to the solving the dynamics fully. Remember, I said I'm going to do everything in the diagonal case because it makes life easier here and faster. So all the weights are also, these P and Q are going to be diagonal quantities. And I'm going to define this degree of freedom term S, which is PQ, this product of this quantity as this S1 to SD. And similarly, the data matrices, the X covariances are also diagonal by definition. And this S infinity term, the fixed point, is also diagonal, again, by construction, what we've done. So once having done all this, basically the whole equation that was a matrix differential equation decouples into these dynamics of each of these diagonal elements. So we get this 2D dynamics, D for P, D for each element on the dynamic. So these are like 2D, one-dimensional differential equation. And in fact, what we've shown before is what matters is their product. So S alpha. So we can actually use the definition use this differential equation to write the dynamics for the product S. And actually from here also see that we get an effective time constant, which is different for each value in the diagonal. Already this is interesting, meaning that whenever S alpha, meaning the final value, the empirical value is large, the dimension along which the X varies the most, that is the dimension that is going to be have the shortest time constant, meaning that it will take a long time to evolve. And we will see that in a second. So this is the final kind of solution, differential equation that we need to solve. There are D of them. And in fact, this can be exactly solved now. And we get something like this. if you look at it, this is basically going to be dynamics. So the whole dynamics for each of these diagonal element is going to look like a sigmoid with a various time point where it goes up. And this time point can also be calculated. And again, you see that there is some separation of time scale depending on the S alpha, which I remind you are the values of, are related to the values of the diagonal element of the X covariances. Different elements on the PQ diagonal are going to be learned at different time. And basically, larger the values of the diagonal in the covariance matrix, slower they're going to be learned. And we will see this empirically. And in fact, okay, we can start with the empirics now. Recall that we said that only two parts of the parameters matter. So I did a simulation for this linear transform models. And here's what we get. This is the empirical simulation of WP on the left, WQ on the right. So only particular element, because for this presentation, I'm showing diagonal case, only the diagonal shows up. Now, these are P and Q here, but what matters, the degree of freedom is P times Q. So, which is the prediction also from the model as infinity. And that we can see here, in fact, on the left is what the model converges to at the end. And on the right is like the immediate analytical prediction for these values for certain choices of various parameter in 5 dimension. On the left, this is where the model gets to, and on the right is what the theory predicts. And as you see, they're pretty much identical up to like some numerical errors. So this is just a fixed point. But what about the full dynamics? In the full dynamics, what we know is S alpha is inversely proportional to sigma. If you remember this inverse term. So larger the value of the diagonal in the slower it will be learned, but the time scale is different. So you get a curve like this on the left. Basically, what happens is the strongest element, meaning strongest value in the diagonal of the X covariance, is going to get learned first. But the convergent, the fixed point is 1 over that. It's a reciprocal of that. So you get this first curve, and then the second curve, and third, and so on. And you get 5 curves because you're in 5 dimension. And the crucial thing about this is this separation of time scale. One gets learned, then the other, and so on. So there is a very different time scale for this learning. And on the right, this is the conservation law. I showed you there is a conservation law where 2 different parameters, basically norm of P minus norm of Q, is conserved throughout the training. And here, this is what you see empirically. On the top, there is the norm of P, norm of Q, on the bottom, norm of P, and you see they're pretty much mirror images. And the difference is the green line, which stays at 0 throughout. And what kind of gives rise to massive degeneracy in the parameter space. Another way of thinking about this is the saddle-to-saddle dynamics. Remember, at the beginning, P and Q equal to 0 is a saddle point. It is a point where the dynamics is very, very slow. So it needs to escape this saddle point, and the saddle point escape happens at different point. It escapes the saddle point and goes to the global minima, and this is when it does that rapidly. And this is what you see of these curves staying at 0 and then suddenly transitioning into their global fixed point, which will correspond to this learned algorithm. And now to try to relate this to real world empirical phenomena, I'm going to go back to a real world example of prefix matching. So anthropic trained model for prefix matching, which is basically if it has seen a word, 2 words together at some point in the context, it needs to be able to predict that. So instruction came after node, so it needs to predict instruction when the query is node. So basically, it needs to look back and see what came together and predict it. In some sense, it's a much simpler task than regression. And here's what they found, that the models are able to do it. Well, in their case, only 2 and 3 layer models. But there was this sudden appearance of this ability early on, and it was kind of happened with this kind of jump in the loss. There's a plateau and then a jump. And this was sort of interesting. They called it like a phase change. I don't think it's a phase change in the technical sense. Nothing I showed you before was a phase change, but it happened rapidly. They call it phase change, and some qualitative point stands, which is that this ability for prefix matching happened very rapidly. And in fact, we get the same case in same situation in our case. Okay, before going that, let me relate it slightly back to the work that I did last summer, which is to show that at these points where the loss is changing and there is some merging, what happens is the effective rank, which is the kind of distribution of the singular values of the weight, meaning basically the diagonal elements in our case, their entropy, their effective entropy decreases. So in these plots, these are for real world models, and this generalizes for more complicated models too. What you're seeing is that there is an effective drop in entropy that aligns with this golden part, which is when model is able to do the task. And basically, when the model starts doing the task, there is some decrease in the entropy of the parameters. And both of these phenomena have an explanation. Firstly, for the loss, on the left, you see an example case in this linear transformer model. And here it's completely clear why this is happening. It's basically because there are two spectral values, these diagonal values that are evolving at two different time scales. So one evolves and that decreases the loss. And then it takes somewhat of a time the second one to start evolving. That's why you get other one. You get this kind of plateau and the drop of the loss. And on the right, you see this. If you look at the effective entropy, you see this kind of drop in the effective entropy or effective rank of this model also in this linear model. And this is also, again, happening due to the separation of timescales of learning. I see that I'm at my time, but I will just take a few more minutes to kind of highlight what are the takeaways from doing all this. First, there is a simple model that does in-context learning for regression, and we can fully solve for it. Second, it exhibits this nonlinear spectral learning dynamics. And there are various reasons to think it might be somewhat universal. People have done a lot of empirical work in this kind of thing in more deep networks, not transformers. And it seems to be sort of universal for an even complicated model. And in particular, the separation learning is fundamental, and it happens in saddle-to-saddle idea, right? Like the model just gets stuck at the saddle, and it needs to slowly and gradually move away from it. So there will naturally emerge this like kind of diversity of time scales in its learning, and this is also what you see empirically in many trained transformers. Reveals one mechanism for in-context non-plastic learning. And here is a point that I want to make that might be somewhat practically relevant. Maybe this can inform model evaluator about appearance of new ability, because basically we can empirically track when these singular values are evolving. You can very simply, without doing complicated experiment, look at the spectrum of their parameters, see how they're emerging, and you'll see this separation of time scale and this kind of drop in the effective ranks. And basically, as some parameters saturate and others learn, you get a series of time points of drops in the effective rank. And you can kind of take these points as a point where some ability or feature might show up in the model, or at especially crucial times to do evaluation, to look in more depth what the model might have learned. It gives us some more fine-grained understanding and so on. Okay, now limitation. All these things, it says nothing about the kind of real-world function and the properties of this function that the model learns. Says nothing about what exactly the model might do in like actual real-world context or its capabilities, and basically doesn't give us handle on the kind of thing it does. Like it tells us how it might learn, but not what it might learn or what kind of capability it might have. And of course, the whole thing is highly unrealistic in many ways, with the choice of loss and model architecture being linear and so on, with the goals of capturing something universal, but it is not going to capture many other things. And it has a wide phenomenology, but there are many things it might fail to capture, as broking and so on. But obviously, there are better doing models that are still solvable that one can work with. And there are various next steps, which I'll just list and not go through. basically all these phenomena probably show up in these models: Bayesian-rich learning, collapse of the parameter space, non-trivial response to initialization, generalization error being interesting, different kind of SGD noise, and outer distribution reliability, and so on. Yes, I'll stop here. Thank you.
Hey, thank you so much. This is a really great talk. So I'm gonna give space for some questions, either from the room here or from the chat. Yeah, any participant, either feel free to raise your hand, put a question in the Q&A, or if you're in person, you can also just speak up. We have like 5-10 minutes for questions, so. Yeah, one question I want to ask is, yeah, roughly, my understanding is that, like, in-context learning is something that usually specifies like a wide range of phenomena, and there's always like some confusion as to what counts and what doesn't. And I think this like linear extrapolation thing is a super interesting example. I'm curious if you could say a little bit about how much you think these lessons generalize to like more complicated cases of in-context learning. And yeah, like both like more complicated models, which you can still kind of imagine fitting a model to the data, but then also cases where it's like not even well clear if it's well understood as fitting a model to the data. Like, for example, if you have something that can start playing chess well in context, or if you have something which can do like reasoning context using text, like, do you think that what you're saying here has lessons to those kind of settings?
Yeah, it's a good question. I think there are various examples of the kind of task that transformers can do, which can be formalized and thought of it in this way. I think one obvious extension is doing something like filtering or like Markov chain predictions and things and so on, where there is some natural way of defining what in-context learning might be, that there is some structure, input-output relationship, or next relationship to the next token, and so on, and defining in-context learning as some relationality between either two pairs or consecutive pairs, and so on. I think when it goes to like more abilities that all our people invoke in context learning as an explanation, I think there is possibly something more interesting going on. Like in this whole thing, I have not talked anything about memory or something stored in the parameters that might be useful in a more striking way, and so on. And I think many things that can be defined as algorithms, such as like in-context regression or like even classification, Gaussian filtering, and so on, can be understood in sort of the framework that I presented. But I think more complicated things, and it's an interesting question, if for more complicated things, there has to be multiple and different kinds of algorithms stacked on top of each other to be able to do those things, such as in-context reasoning and so on. And I think it'll be interesting if it is possible to even solve a model that can learn multiple algorithms. And because this is what we imagine with real world model, it can do in-context regression, but it can do various other things as well. So this one model has stored ways for ways to learn various different kinds of algorithm and not just one.
Interesting. Yeah. I'm going to quickly see if there's any questions from anyone else. I don't want to hog it, but if there isn't, I'm very happy to ask again. Okay, doesn't seem to be. Yeah, this is interesting. I guess like one reason why I'm asking this question, and one thing that I think it relates to some things that other people are doing, sorry about my phone, is that yeah, I feel like maybe this is also just like a little bit of a remark about this kind of research in general. It seems like there's like lots of these models that we can make of like ways that these systems try and identify and solve toy problems. And you can come up with like quite different types of toy problems. You come up with like these regressions. And then there's like, I don't know, like someone else who did the affiliateship was looking at trying to model like epsilon machines and these like little finite state automata and what kind of things they produced. You can maybe look at like Boolean circuits and thinking about the cases in which they learn Boolean circuits. And in each case, we find that transformers kind of like implement something that kind of makes sense for these things. But one thing that's interesting is that trying to understand any one of these in terms of any of the others is usually incredibly confusing. Like if you try and understand a finite state machine in terms of some regression, it doesn't make sense. Same with a Boolean circuit in terms of a regression, or a regression in terms of a finite state machine or something like that. And so in this weird regime where like we have these models of reasoning and we have these models of this more advanced behavior that this system seems to be doing, but the model seems to be like so specific and like narrow in their scope that they can't even account for the behavior of the other simple models.
Yes.
I'm wondering if you have anything to say to that, or if you have any reason for optimism in light of.
So I think like I think the reason for optimism lies not in the learned algorithm. I think almost in for me, the way I think about it, the way the transformer learned to solve the linear regression or these tasks is secondary, like the learned algorithm is secondary to the dynamics. Because I think what could potentially generalize from what I said was the way it learned, like the separation, a time scale of learning and so on. And I think this has been repeatedly observed in various different contexts that are radically different. But I think like the fact that this particular toy model learned this algorithm, I wouldn't make much of it because it's sort of contrived and the whole thing is kind of set up in a way we can solve things and so on. But I think this is also why answering what is the algorithm or what are the things that learned with this toy model, I think is not so helpful for that. But perhaps for answering question, how does it do it? What is the temporal dynamics and so on? I think in this whole work, I didn't emphasize, but the part that's new is the temporal dynamics of learning. People have observed this kind of learned behavior for various tasks across a range of things, but the dynamics hasn't been solved for exactly. And this dynamics sort of have this phenomena that don't rely on the details. Somehow the dynamics become macroscopic, so that what really matters is that there are these saddle points and global minima, and the dynamics flows through these, and they give rise to some sort of perhaps universal feature that might arise in very different kind of settings of learning also.
Yeah, that's super interesting. I'd love to see this kind of work extended to like very different models that are learned, like seeing.
Yeah, I'm thinking about like absolute machine kind of direction too, and I think.
Nice. Yeah.
Probably, yeah.
We should talk about that. Yeah. Fernando, who's doing the affiliateship now, is doing work on that, so you guys should check out that as well.
Yeah, I mean, I must say this whole line of work is like very influenced by people like Andrew Sachs, like and Surya Ganguly, who did first exactly solvable models in like deep networks, and like pretty much the whole line of reasoning here and thought are kind of inspired and taken from that kind of work.
Very nice. All right. Thank you again very much.